Hey folks, welcome to this episode on the factors affecting the rate of the reaction. So, when we're looking at reaction rates, what we have to do is we have to look at what factors are actually going to increase or maybe just have an effect on the rate of the reaction. Now, what that means is that if we're trying to increase the rate of the reaction, what we need to do is we need to either create more collisions, harder collisions, or we need to have a lower activation energy. So remember that reactions occur when collisions occur, and so we need to have an effective collision. Again, an effective collision is something that will hit in the correct orientation and also overcome the activation energy. So if we have more collisions, for example, we'll be able to have an increased probability of having effective collisions. Same thing with harder collisions. So if they hit harder, there's a greater chance that, well, first of all, if they're going to be moving harder, it's probably as a result of an increase in temperature, more kinetic energy. So in this case, not only will they be hitting harder, but they'll be hitting a little bit more frequently. So if they have this harder collisions, that means more kinetic energy will be able to turn into potential energy, therefore being able to overcome the activation energy. Or the last one is that we have a lower activation energy, and this is in the form of a catalyst. So in this case, the amount of energy required to initiate the reaction is lower, and therefore more particles can overcome it. If you remember our Maxwell distribution, we have something like this. If we have, for example, this is our EA of a particular reaction. If we have a catalyst, it might actually bring the activation energy down a little bit. So this would be our EA of a catalyst. In the first example, only these molecules were able to overcome the activation energy. If we lower the activation energy somehow, all of these molecules will now be able to overcome it. So, we have 6 factors that affect the rates of the reaction: chemical nature, concentration, the pressure of the gases, which is related to the volume, the temperature, the surface area, and the presence of a catalyst. So, what's the chemical nature of the reactants? So, when we look at this, we have to look at the reactivity of the particles. Now, remember, some of them will be more reactive than others. If we go back to our activity series, we saw that that's just the way it goes. For example, lithium is much more reactive than copper, for example. That goes back to its atomic structure. We also have to look at the state of the matter. When we're talking about solids and liquids, they're a lot less reactive because the solids, for example, have a high surface area, a low surface area, as in they only have the surface that's exposed to the liquid that would be able to react to this area over here, any of this area over there. Not only that, but solids and liquids also have a lot of intermolecular forces that would have to be overcome in order to react. So typically gases and aqueous ions tend to be a little bit more reactive in terms of their rate of reaction. The bond types, again, some bond types are harder to break than others, so we have to look at that. Ionic species are generally a little bit faster because they're already in ion forms. Remember that if we look at aqueous ions, if we put these ionic species into water, we'll be able to create these aqueous ions. And again, because of that, they're able to be attracted to one another and other molecules. Bond strength, if we have to break a double bond versus a single bond, we're going to have a little bit more energy in terms of breaking this entire double bond. So what that means is breaking up both the pi bond and the sigma bond. And here we'll just be breaking down the sigma bond. So again, the more the more bonds that we have, and the stronger the bonds, the slower it's going to take because we need more energy to actually break that up. And finally, molecular size. In this case, the larger a molecule is, again, it's going to be taking a little bit longer, so a slower rate of the reaction, because in these longer molecules, even this is just carbon and hydrogen, we're going to be having London dispersion forces. Remember the factors that affect London dispersion forces, it's the size and the shape. So even though this might be a straight chain, it is a lot bigger, which means that they're going to have more intermolecular forces being formed. Again, all that requires energy if we want to break it up, which is going to take a little bit longer to do so. Second thing is concentration. Again, one of our points is either we make the collisions harder, we increase the collisions, or we lower the activation energy. In this case, what we're doing is we're increasing the probability of collisions. So if we had a container that was this big and this kind of volume, and we had these species, they'd be bouncing around, and they would have the odd chance of hitting each other. If we kept the size of the container the same, and we increase the concentration, so in this case, this is our volume. If we called this 1 liter, and this was the same 1 liter, if we would see this, in this case, these would be the moles of the green. So we'd have, let's say, for example, 4 molecules, or we can represent in a bigger sample, 4 moles of green and then 4 moles of orange. they would have a chance of hitting. But again, in here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 11 moles of green, and I would assume that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 11 of orange. So what we've done in this case is that here we had moles per liter. Here we have moles per liter. Same volume, but a lot more mole in there. So the chances of collision between this is greater. Because we have an increased chance of collision in here, we have an increased chance of effective collision, which is where we will be creating our products. So again, concentration is another factor. Now, pressure, if we go back to Boyle's law, pressure doesn't really have anything to do with the solid and liquids because the liquids and solids are pretty much incompressible. So when we talk about pressure, we're really talking about the gas. And again, if we have this volume over here, and we have all these moles over here, and we reduce the volume, in this case we'll reduce it by half, we have just increased the probability of that these molecules or gas particles, whatever you want to call them, will have of reacting or colliding with one another. If that collision is effective, then we will see more product being formed. So again, if we see this, you can see that our rate in this case and our low concentration, low pressure is a lot slower than the rate that we see from a high pressure. So you can see that it's a little bit less rise over that run. Here we have a lot more rise over that run. So this reaction will take place a lot faster than this one over here. Temperature is another one, and this increases the kinetic energy of the particles. So here we have a Maxwell-Boltzmann distribution. Our original one in this case was this line over here, this black line just over there. And in this case, we see that, again, most of the particles, remember the area under the curve shows the number of particles, most of the particles have an insufficient amount of energy. And as we go and we see that we have a certain activation energy, that's denoted by this kind of dashed line here, and only this amount of particles can actually overcome that activation energy. Now, if we increase the temperature, we actually increase the number of particles that have sufficient kinetic energy to overcome that activation energy. Generally, we increase the amount of kinetic energy they have across the board, which is why we see this shift going downward and to the left. So we see it going from here, this high peak, to a lower peak, but we also see it progressing this way. Now, as it does that, because the area under the curve stays the same, the particles don't change, what we see is that we see a greater distribution over here. So initially, we had this blue portion that could only overcome the activation energy, but if we increase the temperature, we have this portion now that can overcome the activation energy. So yes, you do have your original amount, but then you also have this added amount when you have increased your temperature. Our surface area is also something, if we look at surface area, the area that is exposed to the other reactants, the other reacting reactants, that's the area where you can actually have a reaction occur. So if we had, for example, they're talking about a marble chip, and we look at this structure here, it's only these surfaces on the outside that can actually that can participate in a reaction. Everything inside is unavailable because it's locked in, if we want to say it's landlocked. Here, if we actually break this marble chip up into individual pieces, okay, you take this and we break it up into here, now all these particles can not only just interact with the edges, so if we have this outside edge, this was the original outside edge. We have these ones here, this, with this, and this. When we break them up, we now have these edges, this one over here, 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 oh, there shouldn't have been one there, and all of these ones that are now available for reaction. So as we can see that as we break it up, we are increasing our surface area and therefore increasing the probability of a collision, and again, therefore, increasing the probability of an effective collision. So you can see here, this is a coal mine. In this case, there was less surface area, and you'd see that there's a little bit of smoke, but as the surface area increased, it would turn into a powder. You can see the amount of reaction was a lot more in the same amount of time. You could see by the energy over there. Now, a catalyst is something that will also speed up the rate of the reaction, but it does so by altering the activation energy. Now, a catalyst, just to remind ourselves, it's a substance that doesn't actually get used up in the reaction. It can be used, but eventually it will always come back to its original form at the end. So when we look at this, To increase the rate of reaction, we need to either increase the number of collisions, make them harder, or lower the activation energy. And what catalysts do is they do the last one. They alter the activation energy. Now, one thing that you have to keep in mind, now this is important, catalysts do not lower an activation energy. They do not lower an activation energy. What they do is they offer an alternative route with a lower activation energy. So if you kind of think about it, if we had a mountain like this, a catalyst wouldn't be able to just lower the mountain. But what a catalyst could do would be to provide a tunnel that you could go through the mountain. So if you had to go from one side to the other, they wouldn't. You can't shorten a mountain or make it smaller, but you could put a tunnel through it. So this would require a certain amount of energy. And again, if you had a tunnel, you'd start here, end up here. That's where you want to be. But the amount of energy that you expel is a lot less. So again, these catalysts, they offer an alternative activation energy, a lower one, and therefore it takes a lot less time for this activation energy to build up. Because it takes a lot less time, the reaction will proceed at a faster rate. So in this case, again, when we talk about a catalyst, it doesn't have an effect on the kinetic energy of the particles. Here's our Maxwell-Boltzmann distribution. Remember that if we had an increased amount of temperature, we would see this. So it doesn't actually have an effect on the kinetic energy like temperature does. It stays the same. But what it does is it lowers the threshold that the particles with a certain amount of energy need to have in order to start that reaction. So initially, uncatalyzed, we had this amount. And only these particles in this area were able to have enough energy to overcome the activation energy and actually start the reaction. When we provide an alternative mechanism, an alternative route with a lower activation energy, now we've opened it up to all these particles, which initially didn't have sufficient amount of energy, but now have sufficient amount of energy to overcome the activation energy and start the reaction. So having a catalyst doesn't actually change the enthalpy of a reaction. Remember that the enthalpy is a state function. What that means is that it only depends on the initial and the final conditions. And so if it's going to be an endothermic reaction, it will constantly be an endothermic reaction. In this case, our delta H would be negative because our products are lower than our initial reactants in terms of potential energy. However, the speed at which this reaction would occur would decrease with a catalyst, because we could have more particles with sufficient amount of energy to overcome this activation energy. So again, it doesn't lower the activation energy, it provides an alternative route with a lower activation energy. This allows more particles to collide effectively, leading to effective collisions, and therefore increase the rate of the reaction. So one of these processes that uses a catalyst is called the Haber process, or the Haber process. And this is using iron, potassium oxide, and aluminum oxide as a catalyst to turn this atmospheric nitrogen into ammonia. So we have nitrogen and we have 3 mole of hydrogen. And what happens is that these particles could collide with one another, but instead they use this bed of iron, aluminum oxide, and potassium oxide to actually do the reaction. So you can see that they latch onto this catalyst, they break up, and then they reform into the ammonia. And so this catalyst allows this reaction to happen a lot more efficiently and a lot faster. And again, we can also see it in different processes as well. So when we create sulfuric acid using the contact process, we're going to use a vanadium oxide to allow this reaction to happen. So you can see that that catalyst is actually used in the second step over here. We go from sulfur dioxide plus oxygen to sulfur trioxide. Same thing in the Oswald process. To create nitric acid, we're going to be using a platinum rhodium catalyst in our first step here, going from ammonia and oxygen to nitrogen monoxide and water. We can also see it in biological enzymes. So when we look at this substrate and the active site, here we have our enzymes, which are just a bunch of proteins that will increase the speed of reaction. So enzymes really are our catalysts. They're just a substance, they're a protein that helps us make these reactions go faster. As humans, we need things done very quickly. So we can expedite this process by using our enzymes. So in this case, our substrate will bind onto our active site, and in this case, they become changed. They have some kind of they undergo some kind of chemical reaction. And here we have gone from one and making it to two, and then they finally separate. So this enzyme really helps us speed up the reactions that occur in our body and as we need them. In our cars, we actually see catalytic converters. So in this car over here, we'd have our muffler, and just before that, we have a little box that actually takes engine gases and tries to convert them into something that's a little bit less toxic. So in the catalytic converter, we'll have nitrogen being made, oxygen being made. We'll also have taking our carbon monoxide and turning into carbon dioxide as well. So we try to reduce the amount of noxious gases coming out of the tailpipe by using this catalytic converter. Now, in this catalytic converter, you have a ceramic mesh that's plated with platinum, palladium, and rhodium. And this, again, just like we saw before, acts as a substrate where these particles can actually bind onto, so carbon monoxide, oxygen onto the substrate. They can break apart, reform, and create a new molecule. So outside, you shouldn't have any noxious gases that can really harm you. Again, when we think about this muffler is moving tons of gases through this part of the engine from the combustion reaction to the muffler, and it happens at a very, very short period. So you actually need this catalyst there. Otherwise, this reaction would have been just simply way too slow, and you'd still produce seeing things like carbon monoxide coming out of your tailpipe. So thanks very much for watching. We'll see you next time.